energy method. Particles A and B, masses 2.4 kg, 3.3 kg, and angle theta degrees horizontal, and particle B hangs 1 meter above the ground, friction mu here, the theta is 30, show that mu is 1.01. So first of all, we need to identify the forces. We have weight downwards that can be split into W cos and W sine, and we have weight of B also, and because of this WA cos, we have this normal reaction force, which is the same because sigma F in this direction equals 0. We have the normal reaction force acting on A. And now, since we have R, we have mu, we can find the F. F is mu R. And we also have tension. So since this B is going down, this A is going up the slope, we have the friction down the slope, of course. Okay, so to find the mu, we can just use FBD of all to make it fast. Sigma F equals 0. The clockwise equals counterclockwise. So the forces that make the pulley rotate in this direction, we have the friction and WA sine, and yeah, we have tension also, but actually they cancel out. And the force rotating in this direction, that's only the weight of B. Okay, so again the tension cancel out here actually, and we can find mu, so we subtract WA sine from both sides, divide both sides by WA cos, and we use the W equals mg formula, and actually we can cancel out all the g here. So the mass of B, mass of A, angle, mass of A, angle, plug in the calculator, use the calculator, and we get this in exact value, or in 3SF. It's proven. Part B, theta is 20 instead, so this is not in equilibrium anymore. The system is released from rest, so the B is gonna go down. So previously it's in equilibrium, but limiting equilibrium, so it is almost moving. Okay, so on the point of moving up, that's why without friction the object will move up, which means the friction must be down the slope. So here the B is going down here, and the A is going up the slope. That's why we have this friction down the slope. Okay, so the fastest way to answer this question is to use energy method. So total distance traveled by A before coming to instantaneous rest. So the B is going down 1 meter, the A is going up 1 meter. When the B is about to reach the ground, it has velocity, exactly the same velocity for A around here. After traveling 1 meter up the slope, it has some velocity. Now after B is on the ground here, the A is still moving up the slope because it still has velocity. So it is still moving up the slope until it stops around here. Okay, and when it's moving in this direction here, the string is slack, right? So if we use energy equation, when the A is going 1 meter up the slope, we have energy lost equals energy gained. For the energy lost, because the B is going down, we have the potential energy of B lost, energy gained, because when B is about to hit the ground, it has velocity. A also has velocity, the same velocity, Okay, so same string means same acceleration, same velocity, same displacement. So we have kinetic energy of A and B. We have potential energy of A because it is going up the slope, and we have thermal energy because of this friction force. In the end, the object is going to get warmer. So we cannot use the energy equation until the end when B is on the ground and A is moving here, because when B is touching the ground, we have some energy lost and we don't know the amount, so we cannot use that state. We can only use the state just before B hits the ground, and when A is moving only 1 meter up the slope, it still has velocity. This is the final state we are using. Okay, so for the delta PE, we use mgh, mass of B, G, so the h B is going 1 meter downwards, and for delta PE of A, we have mg h of A. Now for the h of A, this 1 meter here, 1 meter is the diagonal distance. When we're finding potential energy, we have to use the vertical distance. That's why we use not 1 but 1 times sine theta. So that's why the vertical distance for A is 1 sine 20 degrees. And mass A, mass B, velocity, we're looking for velocity. And the thermal energy is the work done by friction, so friction force times the diagonal distance. And this is the mu, this is the m, so this friction force is mu times r, but the r is w cos, so this is mu m g cos times the distance, which is 1 actually, so actually we have the distance times 1 here. Okay, so now we can find V. Just use your calculator. Because this is not exact here, use many SF. Not exact, use many SF. And we subtract this from both sides, divide by this, take the square root. We have the velocity, we use the positive value. Okay, so when B is going down, just before B reaches the ground, the velocity of B and A is this. Okay, now we're analyzing the energy method again when A is going up the slope. Okay, so when the B is about to touch the ground, it has velocity. A also has the same velocity, but A is still moving up the slope. So we need to find the distance traveled now from this point to this point when the velocity is 0. So when A is going from this velocity to 0 up the slope, energy lost, energy gained. Energy lost because from this velocity to this we are losing kinetic energy. Energy gained is going up the slope, we have delta H, and thermal energy because we have friction. So to find the distance, we plug in 1/2 mv squared mgh f times d. Actually we can cancel out all the m here, and the height is vertical distance, so the diagonal distance times sine. For the thermal energy, force times diagonal distance. And here we factor out the d, and then we divide both sides by the brackets, and we plug in the numbers. This is the velocity and the angle and the g and the mu, and use a calculator. We get the additional distance traveled before A stops. So the final distance, the total distance traveled by A is 1 plus this, or in 3SF 1.03 meters. Right, so this is the fastest way, but we can also do it this way if we want to use energy method,